For our last talk for this afternoon, we're lucky to have Nika Haghtalab here from UC Berkeley. Nika's worked a lot on all aspects of learning theory, and today she'll tell us about multi-objective learning.
Great, thank you. Thank you so much for clapping for me before I do anything. So today I want to talk a little bit about a theory of what I call multi-objective learning. There are many different sort of definitions and expectations of what multi-agent learning means. That's why I said a theory of multi-agent learning, because this is going to be the theoretical perspective that's going to be not useful at all. That is actually a joke. But anyway, let's get to why do we want to talk about multi-objective learning. And I'm sure that you've heard and you've seen a lot that, oh, today's world, we have so much data. There's like so much that we can be learning. There's just a lot of data. I want to take a slightly different perspective that while we certainly have a lot of data, also what's happened is that this data is both coming from very different heterogeneous sources, and people who are providing it are doing it because they have very specific needs and wants from this data and the outcome of the system. So it's not just that we got a lot more resources that we can spend for free, but actually we have to think about the needs of the populations that we are trying to represent. So what is some kind of a picture you can have in mind that I think would be helpful for today's talk is that the learning algorithms we are thinking about a lot of times are sitting in this space of needs of different agents, different data sets, perhaps. You can think about a data set or a learner or a task of learning as, for example, a hospital or a medical center that represents a part of the population. So maybe a hospital that's more about children's hospital and children's needs and diseases, or one for an elderly, or perhaps one that is focusing on heart or renal problems. So these are definitely different types of populations or different learning tasks, different data patterns, different even objectives, essentially, that these hospitals are going to have. And if you're going to use their data, what we really want to do is to also be able to provide the types of learning guarantees, to learn the tasks that those hospitals and those people represented by the hospitals are hoping to receive. So have in mind these kinds of subpopulations or learning tasks that have their own possible distribution, own possible wants and needs. So what happens as we have these more data, more stakeholders? Essentially, the picture I'm trying to build here is that we're going to have more objectives. So these are that we're going to have learning guarantees that hold for these individualized objectives. What are some of these objectives? Well, the objectives are part of dealing with these new challenges coming with objectives is the ownership of data. Data itself is spread across different sources, usually heterogeneous. Those were the examples of hospitals and different types of subpopulations. What about learning guarantees? Well, the solutions that we're coming up with also have to respect the needs of those populations. And usually they have to be deployed across communities with different localities, populations, threat models, resources, think domain adaptation in some sense. And of course, the resources we are dealing with, they're costly and they have to be provided to us by the people who are interested in these learning tasks. So the way we have to think about this is that are we actually providing right trade-offs between the cost of resources and the learning guarantees to each of the agents who are part of this system. So this perspective of having so many different objectives to be thinking about goes sort of against the typical perspective, maybe I shouldn't call it typical, but the very classical perspective of ML, where we think about on-average guarantees. So what is the issue with on-average guarantees? First of all, it's certainly true that we know a pretty well-defined set of theory, well-defined set of tools for dealing with or providing on-average type guarantees. And they're great, especially when you are thinking about a data that maybe just at random was partitioned in some data centers, or just it has no meaningful structure in terms of whose data was sent to what kind of silo, perhaps. So that's possibly great for a lot of scenarios we're dealing with, but not really the one that I was talking about, where the sources of data that you're thinking about are very much human and organizational. They're highly heterogeneous, and they're heterogeneous across axes and features that actually matter to us, like societal, socioeconomical features, perhaps. In this picture, on-average guarantees are problematic because, in some sense, each pattern of data can be very different, and learning difficulty sort of varies based on the learning task and based on the population you're trying to deal with. And of course, some populations might be easier, some populations might be harder, and this is not something that's a priori known because the ease and difficulty of a learning task very much depends on what other learning task you're trying to perform. So on average, guarantees don't work well in this setting. So what does work well? I'm going to give you examples of what our community as a whole has tried to do, and there are many of it. I'll just provide 2 examples to move away from just on average guarantees and more towards guarantees as a whole at a finer grained level. So my first example comes from when you think about trying to provide prediction that is meaningful beyond on average guarantees. So let's think about the standard setting of prediction. This is, maybe binary classification, regression, whatever you want it to be. I have some function I'm trying to learn. There's going to be a loss associated for that function. There's the expected loss. And the super classical perspective here, one can call it the pack learning or the agnostic learning perspective that says that all I want to do is to learn a function that its error is epsilon, or as good as possible. And this is what classically we have aimed for, but it's not really desirable in settings when you think about subpopulations, because what's possible is that while you might have only 5% error, it's possible that 1/10 of the population is getting sort of a randomized classification, and there's nothing sort of stopping you from providing such an answer. So how do we deal with this? Multiple different sort of groups have come up with different perspectives that I can summarize as per group guarantees. When you think about this as you're trying to do pack or agnostic learning, but now you have multiple distributions, D1 to dk, and what you're hoping for is that for every distribution of interest, your loss is small. So this is going from single to multiple distributions. Okay, one example of what we've done in terms of formalisms. Let me give another example. So this was about binary prediction and accuracy loss. You might want something that is more about calibrated prediction. So it's not just about accuracy, but you also don't want to be biased, conditioned on your predicted value. So an example here would be, again, what's a classical perspective on calibration? And this is a very simplified perspective, almost a caricature of this. This is a lot there. Certainly, calibration has been a lot more rich than what I'm going to present, but a sort of classical perspective could be that I'm trying to be calibrated, meaning that I want to be unbiased, conditioned on my predicted values. For those of you, if you're not familiar with calibration, think about it this way. If you predict 10% risk, you truly want that to mean 10%. So across the people you predicted 10%, 10% of them should actually develop the condition you're predicting. So this, again, the classical perspective, especially in the offline setting, might not be that interesting because essentially what you're asking is for your predictor to know the expected label. So it's not very interesting. It doesn't really mean much for any individual person. And a formalism that takes this and goes towards per group guarantee says that, well, maybe I want to think about subpopulations of interest, this time being captured with sort of classes over my feature set. I call this S. And I'm going to ask not only to be calibrated on average, but to be calibrated with respect to any distribution once I condition on my class. Okay? So this is, again, another example where we have taken the classical perspective and moved towards a finer grained notion of guarantees. And the nice thing about both of these is that you can see here, depending on what S represents, maybe S is a set of all little features or all subsets of features, you can really think about going from completely on average guarantees more towards fine-grained guarantees that could be individual cases. Of course, you have to pay for something about complexity of your class of subpopulations, and that has to come in somewhere. So these are examples of formalisms that have arrived and are sort of examples of the larger formalism I'm going to give today and going to work today with. If you want to pick one of these 2 examples to keep in your mind, keep the easier one, so the accuracy. But a lot of things I say also apply to calibration. So what is the point of today's talk? The point of today's talk is to talk about all of these examples of going from a single objective to multiple objectives as one unifying framework, and then think about how would you attack that framework and address fundamental questions in that framework. And that framework is going to be used a lot for fairness, robustness, and collaborative purposes. I will give you examples of this, but hopefully the first picture I showed you already said why fairness, robustness, and sort of collaboration comes when you think about having multiple different distributions. Okay, so what questions are we going to talk about for the next 60 minutes? Well, the first one is a formalism. I promise I will give you a formalism, and that's what I'm going to do, a formalism for capturing sort of performance across multiple objectives. The second question, very fundamental, is, okay, now we have a formalism. How do we address this formalism, and how do we work within this formalism? And especially, like, we don't want to build everything from scratch. So what can we learn from decades of work on classical learning theory, or all the stuff that Natty told you about? What can we think about it also in terms of what's teaching us about multi-distribution learning? And then, of course, when we are thinking about, these are about how much resources we need, there's also a question of how do we go about procuring those resources in a way that respects the wishes of people who are part of this learning task. So what I will do this talk, I'm not going to go into too much detail. I'll just give you a formalism. But whenever you have questions about if this formalism addresses the application you have in mind, we can still entertain it to some degree. Just once again. For the second question, I will provide a unifying view of multi-objective learning. And I give a powerful tool set. And especially as it relates to this bootcamp, I will highlight some challenges of generalization between offline tools and online tools. And the last part, I'll probably have to skip. But I don't know. If there is time, I'll talk about it. There's already a question?
Yeah, just so I understand the setup, actually.
Yeah.
I'm just thinking of having data. There are multiple distributions I want to do with respect to. Do I know for my data which distribution they came from, or do I don't know?
Okay. Great question. Let me give you a slide, and then I'll answer your question, because I haven't actually given you a formalism. I've just given you an example, but I'll come to that in the next slide. So let's start about formalism. I give you examples, but you do want to see what the formalism is. So let's start there. So the first question, how do we measure sort of the performance of these learning tasks? And I already said you don't want to do it on average. There are lots of problems. So let's move towards the per group guarantees that we discussed. The picture I want you to have in mind is the hospitals with different distributions. So we start with K populations as represented by distributions D1, D2 to Dk. You don't know what these distributions are, but you have sampling access to them. Okay, so you can at will take additional samples from distribution I. There are also possible loss functions. What's a loss function? Maybe the loss function you care about is just binary prediction. There are more complicated loss functions. This is a loss function that is for calibration because you're conditioning on your actual value of a function. Or many other loss functions you might decide you want to put in here. We'll think about it abstractly. If you want to have an example in mind, go with binary prediction. And of course, there's expected loss for whichever loss function you chose on whatever distributions you want to think about. Okay. Now, what is your task? The multi-objective learning framework says that you want to learn a function. We think about this as a single function, happy to entertain otherwise as well. You want to learn a single function that is simultaneously good for every population and every loss function. So this should already start addressing Samari's question. This function doesn't know the identity of the distribution. It doesn't adjust itself on the go. It sort of has to have all of the representation that matters. Single function.
My question was more just about the data that I have access to, like high-level cases from.
Good. Think about it as you're interactively taking samples, so you know where you took the sample from. Okay. So what does this look like? This is for a single distribution, single objective. I said that it's less than epsilon, the error I have. Well, if you want to think about this, is that for a single objective and multiple distribution, I want this to be small for every loss and every distribution. So you just have a bunch of maxes here. Okay? And if you can do this, great. It means that you uncovered something that was of universally good accuracy. Universally means for the set of distributions and losses you cared about. Sometimes this is not possible. So if you take the agnostic perspective on this, it says that, well, do as best as you can. What does that mean? It means that, well, you have a function class in mind, and that function class is worst case over loss and worst case over distributions would have had a certain type of guarantee. You're just trying not to do worse than that. So this is the agnostic perspective, and this would be sort of the realizable perspective. Okay? This is what we are going to be working with. But let me say that whenever I give this talk, I get like 5 questions about people's favorite way of thinking about multi-objective learning. And you're right, there are many different ways of thinking about this. So let me just give maybe 1 or 2 of them. This is what we discussed. This is what I call just multi-distribution learning. Single objective, multiple distributions. Actually, focus of most of the technical tools I give you today. It's just because it already allows me to describe some of the interesting technical challenges. You might say that actually, even for single loss, maybe the version of agnostic I would have hoped to get is to do pair distribution, meet the pair distribution sort of benchmark. So Daniel actually has some works on this as well. So this is, while looks different, you can massage it to put it back in this setting and still work with this setting in terms of the tools that come up. And there are a couple other examples of this where the min and max and all those other things are spread differently. The takeaway is if you have multiple of something, at some point you're thinking about worst case, most likely the tools I'm going to talk to you today will still be the type of tools you want to be thinking about. Okay? Any questions about multi-distribution learning as a framework? Yes.
This is FI.
Great question. Sorry, I didn't notice this. If this was F, it would have been what I call multi-distribution learning. FI is the question one of you should have asked, which is like, oh, what if I allow myself to have multiple different distributions and give it to different sort of sources? So each hospital gets its own function. So this is strictly easier than this. Okay? It's like personalized version. This could be also addressed in the framework that we are talking about, but won't be the focus of today's talk. So Maury's question can be interpreted in 2 different ways. Right. There is something about training, and then there's something about deploying. We know at training where the data comes from, but still at deploying, you might not want to take that into account because you might not know that at deploying time. So this is saying that both versions are very reasonable ways to think about this. Other questions?
There are no distributions at test time. All of the K distributions you will have seen, and you will.
So nothing new, you're saying, right? So obviously, any complex combinations of these would have been reasonably acceptable. But you're saying, could I go outside of the complex combination? And whatever I talk about today doesn't do that, okay? I think it's a very interesting question to be asked. It's good to ask it in a way that doesn't just become, like you can always think about a projection onto a convex set, and you don't want to just go with that. So I think great question as to when can you think about using this and saying something more than what domain adaptation is already saying about going from an arbitrary P to a Q. Okay.
And so here I do know what my subpopulations are, right? Because technically I could have heterogeneity where I might not know this neat D1, D2, DK.
It really depends on what we mean by know. It's a learning setting in the sense that you don't know what is DI, okay? You still have to learn. But you do know what I means. So if I ask you to take more samples from DI, the only way you can do it is because you kind of have an idea about what the subpopulation presents. So that's what I mean. So mathematically, think about it as you're given access to K sampling oracles, okay? So you don't know what the sampling is coming, like what they represent, but you can at will take stuff from it. Exactly. Other questions?
And also like properness is like a big consideration.
Properness, great question. Great question. Another version of the multi-objective when if needed to come from the same set of H, where I specifically put it here as F because that's not what I'm going to do. There are interesting questions about, does it become harder when you have to do something properly? It does. I won't talk about it. Yes?
In the benchmarks, the H star depends on each distribution.
Right, the last line, right? Yes, yes, yes.
But you kind of want a single model to achieve epsilon error for every distribution. How is that even possible if H star I is different?
Like you're saying that this looks great, but there's no way you can do it. Okay. Yeah, so when you make all of these other things, usually you also make some assumptions, like maybe H star I is not the same, but it wasn't completely irrelevant to H star J. So these are typically studied under some additional assumptions about the relationship between the hypotheses. Great question. There are, I can give citation to some works to look at it. I think Daniel has some works on this. We have this paper called Multi-Calibration and Unifying Perspective. Well, that's great. It's always nice when the speaker's phone is running. Yes, I recommend you read either Daniel's paper or read a section on the multi-calibration unifying perspective, because it tells you sort of how you can imagine a lot of other objectives that I'm sure you have in mind, and that's why I put this slide up here in terms of still solving a version of this, okay? So let's not take more time on trying to debate other things that I'm not trying to address today. While all the questions were completely on the right track, in fact, there's a lot of papers in this space. If I don't provide citation, come back to me and I give you the citation for the right paper to look at, for the personalized version, for the proper versus improper version, for other things that I'm not going to cover today, okay? So this is a framework. Why do I like this framework? Okay. Why do I like this framework? I think about this as a unifying perspective. And as you saw, there are a lot of versions of it that I'm not going to address. And this is because it's a bigger sort of umbrella that is trying to cover sort of different perspectives that has come up in the past 5 to 7 to 10 years, perhaps even more. I arrived at sort of thinking about these problems, thinking about collaborative learning. And in collaborative learning, what I mean, or collaborative federated learning, these DIs represent sort of actual agents that own distributions, like hospitals, medical centers with their own distributions, and they're willing to share some resources and collaborate. But you don't need to think about it as collaboration. Another perspective was the agnostic or fair federated learning, where these DIs are client distributions in some federated sense, and you're hoping to provide both fairness guarantees and sort of per client type performance guarantees. Then there is the group distribution robust optimization that kind of relates to some of the stuff that John also talked about, but the group distributional version of this, where, again, DIs are thought about as possible distribution shifts, but you can actively sample from, or you can sample from those distribution shifts, again, for the goals of robustness and fairness. And then I can go on and on and on and on, because this is a very natural min-max framework that keeps popping up. But you could think about it, there's multi-calibration, where it's actually a single distribution, but multiple losses of this form. There is other notions of multi-group fairness, where groups, again, present different subpopulations. There are many different ways of thinking about who are these subpopulations and distributions and losses. So I like to think about this as a unifying framework, rather than talking about the needs of any specific ones of these, what I put on the board. Take care of the unifying framework. It happens to provide improved analysis of all of these questions that have been put here otherwise anyway. So let's go to the sort of the bigger abstraction here. So this brings me to question 2. Now that we've agreed on a formalism, how do we deal with this formalism? How do we play with this formalism? And the question I want to focus this is, how much resources do we need to meet the multi-distribution learning objectives? I moved from multi-objective to multi-distribution just because it simplifies things imagine we are in a binary prediction, just multiple distributions rather than having to deal with many different losses. The techniques are very similar. And in this case, sort of what I want to do is, as much as possible, try to get both insights and also comparison guarantees from the single distribution setting, because that's a classical perspective, right? That's a pack agnostic setting. One distribution is statistical learning. Multiple distributions is multiple versions of statistical learning, and both for the sake of comparison and algorithms and techniques, whenever possible, I refer back to the one distribution setting. In particular, I'm not necessarily committed to any one way you want to solve this. Like, this could have been a single task not written in terms of pack and agnostic learning. I think like a multiple version of that would have been just as interesting. But because I wrote it this way for today, I'm going to focus on both algorithms and sample complexity as what we typically think about, the most classical perspective here. So I'm going to be talking about VC dimension and empirical risk minimization. If this was formulated differently, you want to refer to then tools and algorithms that would have been formulated for the single case as well. And I know that you've seen this, but I still want to just bring you up to speed in case you are a bit rusty on how do you even deal with a single distribution in a pack or agnostic setting. So this is a setting where you kind of recall your goal is that you have a single distribution. You're given a sample set S. You want to learn a function that has the smallest error possible. And the reason what you do here is sort of applying uniform convergence. And in some sense, you want to say that every function in your class you're estimated well, and then concentration and uniform and union bound gives you that. What does this give you? It just says that, hey, if I have enough data, I estimate my losses very well within an epsilon. And if I can do that for everything, then the natural algorithm of choice is empirical risk minimization. I take empirical risk minimization. The VC dimension sort of comes up because maybe I don't want to pay a very naive union bound. And then what I end up with is saying that the sample complexity of this sort of learning task for a single distribution is VC dimension over epsilon squared. If it was finite, it would have been log h over epsilon squared. If you don't like VC dimension or you don't remember it, it's just some way of thinking about number of parameters. Another way I would have interpreted like an error bound or sample complexity bound is to think about it in terms of regret bound. This is just different ways of saying it depending on which community you come from. So this is the classical stuff, what you've seen. If you haven't, what you just recalled. OK, so how do we go from this to the multiple version of this? And the challenge of meeting multiple objectives is, like, you might say, well, just run the ERM. There was nothing wrong with it. Just give it more data. And you know, it's not a bad idea. You could try to do that for multi-objective learning. Just run the ERM longer on larger number of samples. This is a bad idea both in theory and practice, unfortunately. I will tell you in theory why it's a bad idea, but it happens to also be a bad idea in practice because in very natural data sets, you still have tasks that are significantly harder than the other ones. And if you keep just taking larger samples, you don't know where that sample should have come from if you decide on the sample set ahead of time. So you're taking a lot of samples from tasks that were actually easy. These are all the black ones. And the task that mattered and was hard, you're not proportionally taking more samples from it. So this is not a very good idea, unfortunately. But it's not terrible if you took more samples from the tasks that were harder. You just need to know what's easy and what's hard. And, well, another way to think about it is that for theory, average loss is not a good proxy for max loss. And that's why this doesn't work in theory either. So the other issue with this is that sometimes some distributions are not just hard, but they're introducing more noise for other distributions. So you should only take samples as much as needed and warranted from a distribution. Don't just arbitrarily take more samples or weigh those samples higher. So this is what we're going to be dealing with. In some sense, the challenges that I just highlighted are all about understanding something about relationship between different distributions. So if you ignore that relationship, that would be just take a larger sample set and run ERM longer, you're not embracing what multi-distribution learning has to offer to you. So let's not do that. The first takeaway is that to embrace multi-distribution learning, you actually need to do this by allowing interactions in an adaptive sense between your distributions of interest. What do I mean? I mean standard algorithms and settings lack interaction that run ERM on a larger data set. The issue is that number of samples, learning rates, update frequency, all of those, if they're decided non-interactively, what happens is that essentially you're ignoring the relationship between distributions. And any method that is sort of non-interactive in that sense ends up paying a number of samples that scales linearly with the number of distributions you have, okay? My takeaway from saying something like this is that without an interactive protocol, multi-distribution learning is almost as ineffective at saving resources as just learning multiple distributions or tasks separately, okay? This is particularly problematic if you are thinking about collaborative settings, when the point of collaboration was to actually save resources. Yes?
How do you formally define that it's not interactive?
The theorem here that I'm providing is a weaker theorem, essentially, that says if you have to come back to uniform convergence, you have to pay this theta of k. There are some other formalisms of this that say that the number of samples that is taken from DI is decided before and independently of the number of samples taken from DJ. Okay, and that again gives you this. Was that another question? Yeah.
No, I was just going to ask what was the question.
Oh, sorry. The question was, what do you mean by non-interactive? Yeah. Okay. What if you allow interactions, and what do I mean by allowing interactions? I now mean that the decisions you're making about DI, like how many samples to take or learning rates or whatever you want to think about, can be done by also making that as a function of something else you did on another distribution DJ. So if you allow yourself this interactivity and adaptivity that comes with this type of interactivity, then what you're going to get is, at a high level, looks like that the number of samples you took scales logarithmic in the size of the distributions or tasks that you care about. This is not really mathematically written here because there are many different things. Let me actually tell you what I actually mean. Here, in fact, it's even better than log. It's kind of an additive thing that says that you're getting log of h over epsilon squared plus k ln of k. I'll give you a VC version of this towards maybe half an hour from now. This says that the k and the log h would get multiplied, okay? Here, they're getting added. Here, they're getting multiplied. You don't want to multiply them.
What are we assuming, like an ERM oracle for each of the DIs, like in terms of the algorithm allowed?
I'm only considering sample complexity right now, so I allow you to do weird computation as long as you want. So you actually can imagine that not only you have ERM, but you have somehow, especially for the finite case, it's okay. You can just imagine you can do computation on H. But most of the algorithms I'll give you algorithms that can run with just assuming ERM. Let's put it that way. Yes? K is the number of distributions. Other questions? Okay, so I'm going to spend most of the time now telling you how you get this, and then how you get different versions of this, weaker and stronger. What I want to do is start by saying, what do I actually mean by interactive and non-interactive? Which I said, you want to make decisions about one of the distributions after having done something on another distribution. But then, if that's what you're trying to do, how do you even think about interactivity, and why should that help? This is where I think having a perspective from solving a game, from like a min-max perspective, like a game theory perspective, is helpful. So what do I mean by that? I mean that imagine or reimagine this multi-objective learning framework that I wrote for you as a zero-sum game. Well, what is a zero-sum game? Zero-sum game says that I have two agents and one loss function. One agent is trying to minimize that loss function, and the other agent is trying to maximize that loss function. And if you've ever taken a course on min-max or game theory or whatever, you kind of know certain things about min-max, which is that, well, the simultaneous play versus one of them going first or second doesn't actually matter. So in some sense, what this is saying is that, well, if you ever find a min-max equilibrium is going to be what you're trying to be competing with. Because the minimizing guy is trying to find the right function, the maximizing guy is trying to find the hardest distribution, and then you're trying to do just as well as possible with respect to that. So in some sense, what you can imagine is that this was a min-max game. You don't need to think about whether the equilibrium exists or not. It's independent of what you're going to be doing. But that perhaps the tools that find the min-max equilibrium are now going to allow you to compete with it. Okay? That's the perspective we're going to take. Now, what changes here? What changes here is that this is a game. The game matrix would have been the loss, the rows would have been the H's, the columns would have been the D's. Unfortunately, this game is never actually written down because I don't know the expected losses. That's the whole point of learning. If I knew it, I would have just picked the best one. So this is a game that's stochastic in nature. We decide the error rates of different cells in the game, however we want. But then we have to pay for it. So how do you go about now solving a min-max game? For those of you who have seen this material, there is one general way of finding min-max equilibrium, and that is to think about no-regret algorithms. Can I just know who knows regret minimization here? Who feels comfortable with regret minimization? Okay. So the ideas here are the same ones as you have seen in regret minimization, boosting, and many other ones. Using no-regret algorithms, you can find them in max equilibrium. And the idea is that it's sufficient for one player to be no-regret, and the other can be either no-regret or best response. Okay? So this gives kind of three different ways of thinking about what algorithms would have find you your min-max equilibrium. When the minimizer is best response, the maximizer is no-regret, when they're both no-regret, or when the roles are swapped in terms of who is no-regret, who's best response.
Does this machinery require L to be convex?
No. Does this machinery require L to be convex? Not. This is already expected value, right? It's an expected value of little l. Little l does not need to be convex. The fact that you just have expectation is doing that. Okay, so now what's the role of sample complexity? The role of sample complexity comes back to the fact that this game was never written. It's a stochastic game. So the sample complexity comes in two different ways. First is, whenever I'm actually doing anything on this game, I need to know something about it. And that means that I need to estimate the cells in this game. Okay? The cells in this game are estimated through direct samples from different DIs. So that's one place samples come in. The other place samples come in is how fast am I actually, like the no-regret algorithms I'm using, how fast do they converge? The faster they converge, the smaller number of steps I need to take samples. So there is a little bit of a fine balance between these two, and different sort of dynamics take different trade-offs between these two and provide different sort of guarantees. Now, how do interactions help? Why do interactions help? Where does interactions come in? This was just something min-max. This is one approach to think about I'm just going to use the no-regret versus the best response algorithm. What I mean is that the minimizer player, that's the guy who's finding a function with a low loss. He's going to be the best response guy, the minimizer. He's going to pick the best hypothesis HT. What does best mean? It means that, well, he's going to run empirical risk minimization to fit it as best as possible to the sample set that was generated by actions of the next guy. What are the actions of the next guy? Well, the next guy is the maximizer. It's the guy who is picking and mixing weights over the distributions, D1 to dk. Okay? So that's our minimizing guy. The maximizing guy, as I said, he's maintaining a distribution over k. We assume he is no regret, meaning that the weights he's picking, this alpha 1 to alpha k, the mixing weights, have to meet a no regret guarantee. Now, where do interactions and samples come in? Interactions come from the fact that, or samples, let's look where the samples are taken. We take samples to solve the ERM. We take samples because the maximizing guy, to be no regret, he sort of needs to have a proxy of how well his actions have done historically. That's how you run a no regret algorithm. You update your weights based on historical performance. So that's where the samples come in. This is also where the interactions come in, because the way you think about no regret best response is that this player goes, then this player goes, then this player goes, then this player goes. And they keep flip-flopping between the two. So the samples that this guy is taking depends on the samples, depends on the actions of this guy and vice versa. So this is why it's interactive and adaptive. In terms of how we actually think about where the samples are coming from, here, when you're taking samples from this distribution PT, essentially what you're trying to do is to take samples from distribution DI proportional with this alpha IT. Here, you sort of take samples from every distribution that you care about, but you're just like, you have a single loss function at a time that you want to assess. Okay, this is a protocol. I will analyze this protocol, but before I do that, questions about it? Good. So at least the protocol is clear. Now, why does this work? Let's do some simple math. I'm going to make a simplifying assumption, which is essentially realizability, that there's like a single loss function, a single classifier that would have labeled everything correctly, and that's in class. So your min-max loss is 0. You're just trying to find something that is good enough. So let's look at the minimizing player. This is what I told you in terms of protocol, what the minimizing player is doing. One way I think about this minimizing player is that he is doing ERM. So if I take enough samples for the ERM to be meaningful. Now, remember from the basics that we recalled, for ERM to be meaningful, you want something like log h over epsilon squared number of samples from distribution PT. So take this amount of samples, and since everything is realizable, you're going to get a hypothesis T whose loss on the relevant distribution PT is small. This is now a single distribution learning task, right? Okay, so we did that. Now, what happens to the maximizing player? I'm going to be a little bit more hand-wavy with the maximizing player. In some sense, it's not that hard to say that, well, you came up from every distribution, just take enough samples, just Chernoff bound. It doesn't have any dependence on the number of parameters. It's just you have one hypothesis HT, you just want to know how well it's performing on every one of your distributions. Take enough samples from every distribution, have a pretty good understanding of its loss, use that to be no regret. So you do that. Now, what does it mean for you to be no regret? This is what it means. It means that, look, the maximizing player is trying to compete with the best distribution, the hardest distribution. That's the max K. And the choices it's making about PT from time 1 to t competes with this difficult distribution up to a regret. You have K options. When we think about regret, you pay logarithmic in the number of sort of arms. So this is the regret. Why is this nice? Because, well, if I run this long enough, like log K over epsilon squared, this becomes tiny. This becomes some epsilon. This is tiny because of my learning guarantees of my ERM guy, which means that move things across, which means that the hypothesis that I'm learning, this H1 to HT, if I pick one of them at random, then, or pick like the weighted prediction of them, this person, this one, is actually meeting the worst case guarantees, okay? So this gave us a reason for why the worst case guarantees of the classifiers you picked at random would have actually been at most epsilon. This is a proof.
In serializable piece for the min player, could you do even better for
epsilon.
Oh, this is hugely wasteful. Okay, good. So what happened? Yeah. Why did I do this? I mean, this is a warm up. Let's look at the number of samples here. The number of samples here is, I said run it for log k over epsilon squared. Epsilon prime is almost epsilon. Then I also said that take these many samples, log h over epsilon squared. So this is epsilon to the 4. It has the nice thing of BC dimension not being multiplied by k, which is what I wanted to do. But in terms of epsilon, this should have been epsilon, not epsilon to the 4. And you're right. In reality, this is not what you do. Or at least you don't analyze it this way. You analyze it a little bit more carefully, and you can certainly get back the single epsilon in this case. Okay? This is just for the sake of demonstration. Other questions? Okay. So the reason I put this up here, though, is that this epsilon to the 4 is going to come back up. But let me first try to do better. Okay? How would I do better? I want to go back to why even. Oh, okay. So if you wanted to stop, paying attention to anything technical at this point, it's fine. Your takeaway should be that, ooh, online algorithms are cool even if your problem is offline. Okay? But for the rest of you who are a little bit more tolerant of maybe a couple more minutes of technical information, I will take you through a tour of some technical challenges and useful toolkit. And to do this, I want to come back to sort of why did I do this ERM? Or why did I do this very naive analysis? In some sense, the thing I'm trying to do at the end of the day is that I just created this online adaptive process, and I'm trying to understand what my online adaptive process is doing. And my challenge is that it's stochastic. It's based on these stochastic losses, so it's really hard for me to actually know what it's doing. And the thing that allowed me to simplify things a little bit was ERM, in fact, because I wanted to analyze the errors of this adaptive process, especially compared to if I ran this process on the known game with the expected losses. And what my ERM gave me was a way of dealing with correlations between past and future. What do I mean? I mean that in this previous analysis I showed you, what I ensured was that at every step of the way on this adaptive process, I was approximately close to this hypothetical adaptive process that would have been run on the real losses, okay? Because I estimated every loss up to an epsilon. So I was very accurate per time step. But to do that per time step, I spent a lot of effort on taking samples and optimizing based on those samples. So I took, one step at a time, and then a lot of optimization, and then another step, and then a lot of optimization that step. So what's nice about ERM or best response is that it's a loss estimator of very low variance, even though it has a potential bias of epsilon, essentially. And how do you deal with, why is this useful? It's useful because at the end of the day, what I say is that, well, if at every time step I deviate only by epsilon, worst case, I'm deviating over t times epsilon, and I pick my t appropriately and things will work out. The only thing that's unfortunate is that I pay epsilon to the 4. Okay, so what would have been an alternate way of dealing with these correlations between past and future is not to create bad correlations in the first place. What do I mean by bad correlations? Where are these correlations coming in? In some sense, again, let's come back to it. I'm trying to control the overall variance of my stochastic process. And per step, I'm working with some estimators. I said in the previous thing, I made sure that every step was close. But at the end of the day, my goal is to say that the average thing that's happening in the stochastic process is close. That's how you solve the min-max game, the average. So let per step work with these, let me have large variances, but let me not be biased because I don't want to pay t times the bias, okay? How do we do this? Let's take a different perspective. We now think about no regret, no regret. So the ERM guy is no longer the ERM guy. He is now playing no regret algorithms over the function class h. What is he doing? He picks an HT, but for me, now I'm going to control the correlations. I said I'm not going to create a bad correlation. So what do I mean? I mean that I only want it to be no regret. And the nice thing about no regret algorithms is that they never look at the current step. They only look at the past steps. So HT is actually picked before any samples are generated from PT. Okay? So I can even generate a single sample from PT. Now, the maximizing guy is doing what he was doing from before. He's picking PT. He never looked at HT to start with because no regret only looks at the past. But what this says is that because HT and PT were picked sort of conditionally independently of each other, once I condition on the past, then the loss of PT-HT, even if I take a single sample from PT, is a reasonable estimator. High variance for sure, but doesn't have bias. Why does that help me? Because now I can control how to deal with this variance. If I have an unbiased estimator, I have a martingale now. The variance I can deal with, even though it's large per step, over many time steps, on average, it will shrink. I don't have bias to build up. So essentially what this allows me to do is, and there are versions of this that were known before as well, that says that you can the convergence rate you get to multi-objective learning if you play two no-regret algorithms against each other is approximately the empirical regrets of these two, okay? Because you pay the martingale concentration. But it's great because empirical regret is something I understand, I can deal with. In fact, this is telling me that I just need to control empirical regrets that come from multi-arm bandit algorithms. For the minimizing player, essentially I'm in a full information setting where I have many different functions, and I take a single sample and I evaluate every function on that sample, and that gives me an unbiased estimator of all of these functions. Since it's full information, the regret scales logarithmic on the number of options available to you, so that's log of h. The maximizing player is banded information because at a given time, the sample it's taking comes from only one distribution, so it doesn't really know what's happening on the other ones. But for that one distribution, it still has an unbiased estimator. So it's as if like it took one of the arms and only observed what happened to that arm, but not the other ones. And for the bandit optimization, the regret scales linearly with the number of arms. If you put these together, you get the following bound, that now you have epsilon squared and log of h plus k ln of k. Let's pause for questions. Are there any? Yes.
So the final estimator is a randomized estimator.
Mm-hmm. Predictor, you mean, right? Yeah.
And so, what are you? How do I put this question? So it's a randomized predictor. Are you thinking at all about de-randomizing it at the end?
Yes, you can de-randomize it by paying a constant, so it would become c times opt plus epsilon, like twice opt plus epsilon, I believe. If you truly want to de-randomize it, you can do that. And certain domains, you don't need to de-randomize it. Just we can take like a linear combination of it. If you could, then you don't pay that C. There are certainly interesting questions, like how I said that even the question of proper improperness comes up. There's really interesting questions as to if you want it deterministic or you want it proper, like does the rates change? Does the computational complexity change? And I can point you to some papers to look at it. Other questions? Okay. I want to address the elephant in the room, which is this hypothesis of class function. I mean, nobody pays log of h. I'm surprised you let me go this far without complaining. So people don't like to talk about finite VC dimension. Here, I'm trying to sell you on a finite class. Fair. Thanks for letting me run with this. Let's talk about why I did that and what would have happened with the infinite classes. So far, I essentially gave you a naive approach of epsilon to the 4. By the way, that epsilon to the 4 would have worked even without realizability, which depended on VC, and that was the nice thing about ERM. Then I gave you this thing that depends on log of h, and this could have been the Wilson dimension for those of you who know what that is and like it. It doesn't change the question of what about infinite hypothesis classes? Could I have just like run this thing for infinite hypothesis classes and hope that it would have worked nicely? In practice, absolutely, it works nicely. In theory, questionable. Essentially, what you need to do is to make sure that at every time step, there is a net, an epsilon net of PT that you're working for the PT that you're encountering. And the thing is that such a net, like a small enough net, actually exists. And I think that's partly why things work out really nicely in practice. In fact, you could imagine that there is a net for each one of your distributions. You put them together, that's a net for everything that you care about. The size is pretty okay. You know, if you take the log of it, you get this rate, so it's a really nice rate. The issue with this is that we don't know what that net is a priori. And if you were to actually construct a net in a naive way by taking enough samples and then, the usual thing you can do to construct a net, you already spend k times VC dimension, something that we didn't want to spend. So already we talked about some challenges of generalization, right? Essentially, like we are trying to talk about generalizing to k different distributions. Here we are saying that, so there is even another interesting layer of generalizing to k different distributions when you are also trying to generalize to infinitely many hypotheses. So how do you address this? And this was an open question that really bothered us for like, I think I admit for a year, but it was more than that, until we decided that we're just going to write this as a cold open problem, which was a great decision because it allowed others to tell us their insights and technical tools. So what I'm going to be talking about is, I'll give you some insights about like what's the right way to form this question. And then I give you a technical tool that actually comes from one of the papers of Jason, who is right at the door, but is not entering for some reason. Hi. Okay, online versus offline. So what is it that we have to do here is that, or what is the issue with the epsilon nets? Just think for a second, like entertain this idea. I start with an epsilon net for my first distribution, that's my P1. What's wrong with just reusing it for my next mixtures on and on? Like what can go wrong? And well, in a really like bad case scenario, especially, let me imagine these add up to 1. I wasn't gonna put a lot of minus ones in there. You might imagine that, okay, I start with a uniform mixture, and maybe something after a couple time steps, something happens and I realize that first distribution appeared just so hard, so its weight increased while everything else just appeared pretty easy. But the second that happens, then somehow I discover something new and this first distribution is no longer hard and the second distribution all of a sudden becomes hard. And so on and so forth. Like the distribution that's hard keeps changing. The problem, if such a thing truly happened, this would be disastrous because essentially, as you realize that you need to take more samples from one of your distributions, that distribution becomes unimportant to you later on. And then you have to repeat that. And that's not something you want. Like if that happened, you have to sort of, this is problematic because sort of the larger the weight, you want to take number of samples from a distribution DI that scales with this largest weight, because that's how you ensure that you have enough samples eventually to kill that variance. So the problem here is that each of those distributions get a max that is high at some point, leading to the same issue as essentially having to construct a net for each of the distributions separately. So what do you do here? Well, this is the work that that came out recently. So Jason Lee, Simon Du, and I just want to make sure, is there anybody here who worked on this paper? Okay. I did check with Jason, so we can talk with Jason as well. A very interesting work that provides the optimal sample complexity or near optimal sample complexity for infinite case. And the idea here is that you say this bad case doesn't happen. And it doesn't happen when you think about the trajectory of the no-regret algorithm, especially when you think about it as no-regret best response, which is the first algorithm I was talking about. And essentially, it says that it's possible that some of these distributions jump up in weight, but if as a whole I sum over the max weight that any distribution at any time can have, that is not going to be large. That actually can be only logarithmic. So it cannot be k, which would have been the bad case I constructed. It will only be logarithmic. And once you have this, really, it's essentially saying that you can make useful nets out of offline computations in an online way. So I think this is really beautiful and elegant. Highly recommend that you guys take a look at it. I know there are people here who like to think about very concrete open problems. If I were to give you very concrete open problems, this log k looks suspicious. This is something you don't pay in the truly offline setting. You don't pay log of 1 over epsilon. This looks like that. Is it necessary? We don't know. The lower bounds are just VC. And we pay log of h in the finite case. That's why, again, it's not clear if you should be paying log of k. If you like to talk about logs, this is also suspicious. Well, it's not suspicious. We just don't know if it's necessary. The lower bound is VC plus k over epsilon squared. So let's just say all of these logs are unnecessary, perhaps. Who knows? But if you don't want to just think about concrete open problems, but you want to think about actually the agenda, what's left, what's interesting here, I'm going to skip this. It works very well empirically. Let me say that I don't have time to introduce a whole new loss functions for you to sell you on a different, challenges that come up from different domains. But what I do want to go back is that I put 3 different dynamics here. I talked about 2 of them, and we already saw that the picture in terms of trade-offs between them is interesting and not quite clear. Like, is there one of these dynamics that you should be always using? Turns out, depending on the application, not really. And this is not a very well understood thing. It's just that we understand different dynamics for different problems have very different trade-offs. And it's, I think, interesting to think about for the problem of your interest. Maybe it's the adaptivity. Maybe it's the sparsity of something. Maybe it's about, trade-off between generalization and computational complexity. What would have been the right way of thinking about these trade-offs? My point is, if you embrace this game-solving perspective and think about myriad of dynamics that might have been useful and have been studied a lot, you might find that you're learning something new and getting a new way of attacking a problem that you've been dealing with for a while. Okay, so that's that. Any questions? Okay, so we have a little bit of time still, and I'm going to do this. I was thinking that I might even skip it. So at any point, if you want to ask other questions, we'll just say that this is going to be really high-level picture, but more than happy to continue asking questions and talking about these outside of this room after 5 o'clock. What I want to talk about is this question 3, which is, well, we talked about solving these problems while using total number of samples or resources that's small. But what if we were going to procure these resources? So it wasn't just like some arbitrary distributions that at will I took samples and I took as many samples as I wanted, but they're actual agents who are providing those samples. How does this theory of generalization across different distributions works with the theory of incentives of providing those resources? So this is kind of the third of these, which is let's move beyond accuracy as the only objective. And what we're thinking is that agents might also incur loss for actually providing resources we want. Certainly the case in terms of costly resources, like when actually providing a label for a resource is a physical task. You have to dig a hole in someone's backyard to see if their pipes have lead in it. But also certainly the case when there are costs for privacy or other things that just make someone not want to do give you resources for free. So can we make sure that still these collaborative interactive protocols happen when we want them to happen? So how do we think about this? My goal here in this very short amount of time that's left is to tell you that it's highly non-trivial and kind of make this almost like a call to action that this is, I think, really interesting and important to think about. If you're thinking about learning, you should think about the incentives behind learning as well. And for a tiny bit more of a formalism here so that the next few slides make sense, I want you to think about this as each agent or the data distribution. Like I'm asking you to provide a sample set of size mi. So when I talk about an allocation profile, it means there is a vector of these m's, and I'm asking distribution I to give me mi number of samples. And I go back to saying that once I do that, I'm going to go back to a slightly simpler algorithm. It's not the no-regret versus best response. It is the ERM, the original thing that I said that it's not the best thing you do, but it makes it easier for me to tell you what's going to go wrong. And we are still saying that each agent has a minimum desirable expected accuracy of alpha I. This alpha I is the epsilon from the previous slides. So everybody still wants to get something that's accurate for themselves, but they have incentives over which MI they're willing to deal with. So the idea is that we want these MIs like conditioned on actually providing the right solution. We want the MIs to also be reasonable. Let me talk about what could be potentially unreasonable is if you think about an agent I and you ask them to provide a number of samples that would have been more than what they needed to just solve their own task independently and individually. That's unreasonable, okay? So we want to avoid this. Another thing we want to avoid is that part of I's sample set was solely used to sort of meet the objective of another agent. So that's, again, unreasonable because the person who provided resources was not the primary person or individual to actually be benefited by it. There are economics kind of way of capturing these formalisms. The first one, avoiding that unreasonable thing, is called being individually rational, which essentially means that a profile of MI is rational, individually rational, if in the case that agent I solved everything individually without any other help, the number of resources they would have needed individually is bigger than the number of resources they're being asked to provide in a collaboration. So that's individual rationality. The other is something called stability. It's a notion of Nash equilibria, for those of you familiar with that. Kind of like a Nash equilibria that says that this is reasonable if agent I reduces their own share while nobody else does anything. Unilateral kind of deviation from the number of resources provided by an agent would go back and hurt that agent's accuracy. So these are the two things we're hoping to achieve. So our goal now is to respect this, be individually rational and stable, and then say, can I still design good collaborative protocols? That's the question, right? Can my collaborative protocols still save sample complexity? Why do these things matter, you might ask? And I would say that there are notions of welfare of agents. I told you why there are notions of welfare. But the other thing is that there are notions of usability of the system as well. Because if any of these things is not met, either a person wouldn't enroll in the system to start with, or if they do, they keep changing their strategy and maybe collecting less samples, and they sort of mess with the performance of the system overall. So the system becomes really unstable. And this is not just something that happens in theory, or there is a risk of it in theory. Again, if you take sort of these multitask benchmark data sets, one thing you do see is that a large number of agents, like for this example, I guess 60% of the agents think that they could unilaterally drop essentially out fully. And let me just say that even if 5% of those agents drop out, we don't get enough samples to sometimes even meet convergence. So this is a problem. Maybe we don't see it a lot right now because we don't have a lot of control over how our data is shared. But trust me, it's a problem in systems where people can actually opt out. What I want you to take away here is that these things always exist. I can always come up with a way to ensure rationality. And most of the times I can ensure stability, but they do require a lot more resources. One way to think about this is that imagine a task that's so generic that every other task is almost a subset of it, but slightly different. Now, this is a task where optimal collaboration looks very different from incentives. The the optimal thing to do is that this generic guy should just like solve his tasks really well, and then everybody else is going to be benefited. The individually rational thing to do is to never ask this person to provide a single sample, because if everybody else meets their objective, this learning task is already solved. So efficiency and incentives are going sort of against each other. And this is a problem because one thing you can construct is a really bad case where, you remember I was trying to save that blowing up of scaling with k to log k? This says that a slightly different setting, you lose all of that. The optimal collaboration would be 1 over k times of collaboration that would respect the individual's needs. So this is a problem. I'm not going to have time to tell you how to solve it, but I think you should think about designing platforms that allow us to solve this to some degree. And let me just say that, yeah, I'm not going to have time for this, but the overall important message here is that there are algorithms that need to sort of act globally, but have per agent, per objective guarantees. There are many of them. I gave you an umbrella of types of formalisms that you want to be dealing with. And I think this is a really good opportunity to think about theoretical and practical questions as to how to provide such guarantees. That's it. Thank you for being here.
I think we need to be out of here like now. Maybe we can just take questions outside. Okay. Thank Nika again.
Yeah.